My name is Ankit. I'm a senior staff engineer on Affirm's infrastructure platform team, and I have Dan with me today. We're going to be talking about financial workloads on Apache Iceberg. Today's agenda, a quick intro to what Affirm does and what we do at Affirm. What are financial workloads at Affirm? Our data architecture around Apache Iceberg, the patterns we use in pipelines with Apache Iceberg, and how we leverage Apache Iceberg for our replication between OLTP and OLAP storage systems. And at the end, we'll have a lot of time for questions. Some of you may have used Affirm directly through use it as a power user of Affirm, directly using them on any purchases you're trying to make, Affirm card or our savings product. Our mission is pretty simple. It's to deliver honest financial products that improve lives. How do we do that? When Affirm started, we wanted to build something very transparent, where every purchase had a clear end date. There were no surprises or gotchas, and most importantly, the consumer knew exactly what they would pay for. What you see is what you get. We put what is good for our customers first, and we never benefit off their misfortunes. We are, by design, a very honest credit product, and there are no late fees. There'll never be late fees. We focus on giving you the choice of using your credit in a very simple and an honest way. As I said earlier, we want to give you an overview of how financial workloads play a key role into building these financial products that we have for our customers, and what is the role of Iceberg in doing so. Before we get into exactly how we do this, here's a quick screenshot of what our GMV looks like. Our GMV grows between 30 to 40% across every year. Our other metrics also grow 30 to 40%, which is directly reflected in how our data estate or the rows in our tables grow. This is a screen grab from our last earnings report. We're very proud of how we are doing, and we want to continue to grow. With business growth comes the scale problem. A quick overview of numbers. We processed about north of $30+ billion of loans in the last 12 months. Financial workloads to support this financial transactional processing mostly are based off batch pipelines. We do utilize some RPC, external HTTP calls, and some stream processing in there to make sure that we produce financial reporting for our external partners in an accurate and timely manner. Building an honest financial product doesn't just stop at our ability to give credit to consumers. We also have the obligation to make sure we accurately report on financial metrics, furnishing systems. Making mistakes is just not an option or what we should be doing. Making mistakes does a disservice to our users, our merchants, our investors. Having an accurate representation of our financial metrics also encourages our capital investors to join our journey and promote building honest financial products across the global financial ecosystem. Upstream of all our financial workloads is conceptually simple database replication service that allows us to publish a read-only replica to our Iceberg data lake. We're going to get a deep dive into it shortly. Before we jump into what database replication looks like, what our patterns are, I want to do a quick overview of our requirements of our OLAP storage system when we started looking at Iceberg and other table formats. We wanted the ability to time travel. We wanted the system to allow us to build APIs for verifying data integrity. This is a simple one. The system needed to scale for both reads, writes, and provide us the mechanisms we needed to do replication at scale. Cost is always important. You want infrastructure costs to sublinearly grow with your business needs. Security and governance, we wanted to control our data. We wanted to ensure that we own all parts of our data system. Simplicity in operations, if any of you guys have worked on infrastructure teams or with infrastructure teams, you don't want to wake up at the middle of the night trying to figure out what your financial databases are doing or if they're broken or not. Last but not the least, one of the most important things we wanted to do was stop making copies of our data sets. So we wanted to focus on write once and read anywhere across our entire data stack. Next slide. So next up, I want to give you a quick overview of what our data stack looks like. At the center of our data stack is our storage catalog. As you can see, it's Polaris catalog, but it is actually Snowflake Open Catalog, which is a managed implementation of Polaris. Above the catalog are our product services, our experimentation, operations, and analytical services. On the left is where you would see our data producers. The profile is an application developer, ML engineers, data scientists. On the right, we also have data producers, data science teams, analytics teams, business users. All these users primarily access this data through Snowflake. We have other tools, depending on teams and expertise, that allow them to still get access to Iceberg and our data sets in Snowflake. How do we arrive at component choices? Like what goes into our stack and what doesn't? We prefer managed solutions over managing infrastructure ourselves. At the same time, we do want to have an open source alternative for the managed solutions that just allows us to focus on building APIs that democratize infrastructure to rest of product engineering. Our journey to use Iceberg started in 2023. We started working with the Tabular team. That was a small startup. I was building out a managed Iceberg solution. We partnered with them on building the first version of CDC replication service. As of today, we are 100% invested in adopting Snowflake's open catalog. We have brought in CDC replay in-house and optimized the pipeline. We have much more tighter integration with Snowflake where all of our analytics and business users are. At the same time, we are super excited and want to continue to invest in our Iceberg adoption journey. We do want to see how other vendors and companies evolve their offerings around Iceberg. We are super excited about S3 tables, Confluent table flow, and we didn't have the time to update about OpenFlow, so we do want to look at that too. Next up, we want to give you a quick overview of patterns of pipelines around Iceberg, and this is where I hand it off to Dan, who knows better than me.
Hey everybody, as Ankit mentioned, I'm Dan. I'm also an engineer on our Lakehouse platform team. So I'm going to talk a bit about the patterns we're leveraging with Iceberg, how we derive value from them, and then go a bit more in the weeds on our database replication system. So what value are we getting from Iceberg to start with? So number one is data minimization. As Ankit mentioned, time travel is a requirement for us. So in the past, that looked like maintaining many copies of data sets. Keep it from this day, this day, this day. But Iceberg natively supports time travel via tags and branches. We also have the ability to write once, read anywhere. We write to our lake and then have various clients that are able to read from it. It's also much easier for us to accomplish exactly once processing. We're going to take a bit of a deep dive into that and challenges we had in the past and how we solved them with Iceberg. We have a large number of clients that need to read from our data lake. So Iceberg supports this through various connectors. And we use a write, audit, publish pattern to kind of mimic a two-phase commit and ensure that we're only publishing audited data in our financial workloads. So prior to Iceberg, we were attempting to achieve exactly once processing on S3. And the key principles around having exactly once processing are going to be a replayable source and an idempotent sink. With a replayable source, we know that each time we start a job, it's getting the exact same inputs. With an idempotent sync, we know that if a job needs to retry, there's flakes, we're going to get the exact same output. This is challenging on S3. Our upstream tables were changing, so we're not actually getting the same input to our jobs. And then we're subject to partial write issues. So if our job failed, had to retry, we might have duplicate data or have to truncate paths prior to retrying our jobs. But in the world of Iceberg, we're able to achieve this entirely, leveraging Iceberg APIs. So by reading from tags, we're ensuring that we always get the same input data, the same source data. We use merge statements to produce our outputs. So any kind of retries, our writes are entirely idempotent. And so our consumers don't have to worry about any kind of write issues. They just listen for new tags. That's kind of how we indicate that an output is available. We'll place a tag saying, OK, here's the version of the data set that's good for you to read. So how are we leveraging write, audit, publish? If you're not familiar, it's pretty similar to how it sounds. It's 3 steps. We'll write, then validate our data. We'll audit it, run business rules against it, and then finally publish the result for consumers to read from. So to do this, we use Airflow task groups. I'll have a single task group with each phase of write, audit, publish in a separate task. And this gives a clean interface for our developers to retry and recover from each phase independently. It's a clever way to achieve a 2-phase commit, as I mentioned. And why do we do this for financial workloads specifically? Well, developers need to generate financial reports in these workloads. You can imagine there's very little room, actually no room for error as we're dealing with financial data. So developers need to explicitly opt out of validation in this pattern. So this gives us developer ergonomics that encourage validation prior to publishing. Because once a data set is published, that kicks off all the consumers. As if you might have dealt with any kind of complicated batch pipelines, you now have a set of n other processes that are kicking off. So once you have one unaudited data set with an issue, it now turns into n data issues throughout your pipelines. What do we want to do next with Iceberg? We're working on building operational maturity. We're aiming to have kind of the same maturity in our OLAP systems as we have in our OLTP systems today. We're working on developing clearer APIs, making it easy to use these best practices I've talked about. We want to build better abstractions based on domains, as I think Ankit touched on before, kind of our domain organized data sets. And we're continuing to invest in data DevX, ensuring we internally support all of the clients that are available for Iceberg, and investing in our own kind of deep expertise on tuning the performance of our tables. And now I'm going to take a deeper look at how exactly we're using Iceberg in this database replication process we've mentioned. Why exactly do we need these databases replicated? So our financial workloads are moving money, funding the business, and upstream to most of them are going to be our databases. Because the source of truth of any significant event or attribute is typically going to be in a database. That's where we're storing the life cycles of our loans, the transactions we process, et cetera. So our financial workloads often have strict external SLAs to banking partners, regulatory agencies, and whatnot. So we cannot tolerate delays in our replication system, but we also cannot tolerate any kind of data discrepancies. Our financial workloads need to know the state of our databases at a particular point in time, and we can't have any missed events, duplicate events, whatnot. There's no room for replication error. If we miss these SLAs, we're opening Affirm up to both financial, legal, and reputational risk. And so it's important that we have correct data as fast as is needed, but our data continues to grow. Remember that 30 to 40% figure. But our SLAs are not moving. Those cannot grow at 30 to 40%. So it's quintessential that we have the runtime of our pipeline scaling sublinearly to the growth of our data. So prior to Iceberg, we had a snapshot-based database export system where we're literally just dumping these tables on a nightly basis, like selecting the entire database table every day to a new S3 path. So for larger tables, this was taking 2 to 3 hours because Affirm's data just keeps on growing. And we also have sharded databases, right? So between multiple shards of our databases and a large number of tables, and producing a new copy of that data set on a nightly basis, we end up with hundreds of thousands of database table copies in S3. So this is both expensive and operationally complex. We have a ton of data sitting around just in case somebody needs it with all these copies. We also have very large database read replicas just sitting around waiting for these nightly exports. So one of the reasons we had to keep all these copies around is that, as Ankit mentioned, time travel is a big requirement for us. So our users have an expectation of time travel. We often will need to regenerate reports from data in days, weeks, or years in the past. And even on a shorter time frame, our industry kind of works off UTC0 as the end of the day. We'll then have a set of daily pipelines that need to run and send information to banks, agencies, whatnot. So our pipelines need to know the state of our databases as of UTC0. In order to give this to our consumers, we produce Iceberg tags in 8-hour windows. So we're going to be continuously running what's called CDC replication, which I'll talk a little bit about, and then validating, auditing that all the data is made it to our tables correctly before we publish these tags that allow workloads to time travel to UTC0 on the current day or previous days or previous years. As mentioned, we are continuously validating in these 8-hour windows, so we ensure we always have the correct state of our databases as of the timestamp we are trying to tag. So what does this look like in practice? If you're familiar with Iceberg, you know that each write is going to produce a unique immutable snapshot, and a tag is a reference to a particular snapshot ID. So we are performing our replication, validating that all the data there is correct, there's no duplicates, and then tagging the snapshot. So every consumer is reading from this same unique snapshot as of UTC0, UTC8, UTC16. So this is a public interface we provide where our workloads specify the date or time at which they need to read from. And then in practice, we're just using the version as of SQL syntax to read from a particular tag. So here's another look at kind of the replication architecture. I mentioned CDC replication, so that stands for change data capture. So in our OLTP databases, there's something called the binary log, bin log, and that produces an event for every update, insert, delete to the database. We replicate those events to S3 and continuously replay them on our downstream Iceberg database copies. On a periodic basis, every 8 hours, we'll grab a sample from MySQL and validate that everything there is correct. It's made it, we're good. And then our financial workloads and analytic workloads access those tables through our Iceberg REST catalog. We're continuously performing this CDC replication, and I mentioned our kind of write, audit, publish framework. So we will branch off of the current state of the table, so targeting to tag UTC8. This was the database at UTC8. All the data is there complete. And what we really need to do is verify correctness. So we don't expect there to be any issues in our CDC pipelines, but we are operating a distributed system, and distributed systems have faults. So in the rare event that, for whatever reason, data did not correctly make it into our Iceberg tables, we're able to detect it and correct it before we publish for consumers to run their financial workloads off of. It's quite rare that we have to do this, but we always have that fallback. We are not inputting inaccurate data to our financial workloads. So we create this branch, we replay to exactly 8 UTC. Then we pull our sample from MySQL, ensure everything matches there. There's no discrepancies between source and target. If we need to, we'll remediate our data. Once everything's correct, we merge our branch back to the main branch of the Iceberg table, place our tag, and our consuming workloads who are poking for this tag can now proceed via Airflow sensors. So what benefits do we derive from this? As I touched on before, if there are any failures in our CDC pipelines, we're able to remediate it, and we are not violating those kind of crucial external SLAs. We have automated auditing here. There's no manual intervention required on the part of us engineers. We have one logical MySQL table in the data lake for each upstream MySQL table. So in practice, we have our tables sharded across multiple database clusters, right? But there's just a single view in the Iceberg data lake. The amount of time taken to make these data sets available for workloads significantly down. So previous snapshot system, we had 2 to 3 hours. Now we have an SLA of 1 hour. It's significantly cheaper. Costs have fallen by a factor of 6. And on average, the performance of our pipelines reading from these database exports have improved by 40%. So if you can get access to the slides afterwards, we have a whole blog post on this topic as well. All right. Well, next we'd like to just do a few shout outs to the Affirm team. Thank all the people that made this possible.
Yeah. Both of us were people the short straw to do this presentation, but a lot of effort went into building this. So this is a shout out to the team. Thank you, everybody. If you watch this on a recording,